Welcome! In this video we're going to talk about KSP, which is the solubility product constant, and do a couple of calculations involving it. So these problems we're seeing are from page 11 in OneNote, and we're starting out here looking at this table at the top. And KSP describes the reaction of dissolving an ionic solid in water. So what ionic solids do when you put them in water is they break up into their ions. So in this table here in the middle, notice that the reactant in this case is always a solid, and the products are always the ions that make up the solid. So like KNO3 splits up into potassium and nitrate ions, calcium hydroxide splits up into calcium and 2-hydroxide ions. So the reactant's always solid, the products are always aqueous. And when we're writing a K expression, remember we leave out solids and liquids, and it's products over reactants. So in the case of a KSP, which is the K for dissolving, the products are aqueous, so they go on the top, and then the reactant is a solid, so it gets left out. So whenever you write a KSP expression, you're going to notice there's no denominator, and that's because the reactants are all solids. You can see that over there. And if we look at this table here, the top two compounds are compounds we typically describe as being soluble in water, and the bottom four compounds are typically ones we describe as being insoluble in water. And if you look at the K values here, what I want you to notice is that the soluble solids have KSP values that are greater than 1. And if we think about the meaning of K, if K is greater than 1, that means that it is products favored. So we mainly have products at equilibrium, which means we have mainly aqueous stuff. So it favors the aqueous side. So we don't have much solid left over. The insoluble solids have very small KSP values. They are less than 1, which means that the reaction is reactants favored, which means at equilibrium we have mainly the solid form. So when we look at these things, we say, hey, those are insoluble. We have mainly just solid left over. We do not form very many products. So based on the K values, we can quantify that and say which reaction will make the least amount of product. That's going to be the one with the smallest K value, okay, because K is going to be proportional to the amount of product, as we can see in this K expression. So the one with the smallest K value in this case is silver chromate. The one that's going to make the most product is going to be the one with the largest K value, which of these examples is sodium chloride. And thinking about how K relates to delta G, for sodium chloride, we know that the K value is greater than 1, and that means that its product's favored. That means the forward reaction is favorable. That means it's got a negative delta G, and the reaction is favorable. If, in the case of lead chloride, the K value is less than 1, that means that forward reaction is not favorable. And that is why it is reactants favored. So we don't make very much products there. So we've got an example here. I'm going to skip past this. And we're going to go through a couple of these and calculate the molar solubility of a few of these things down here. Okay. And notice that I copied down my table from above, because I'm going to use the values from problem number 1 here. So let's take a look at 5b. Okay, so I'm trying to calculate the molar solubility, and I already wrote out this reaction, but I'm probably going to write it again here just so I can set up my ice chart. So I've got my solid reactant forming aqueous ions. And remember, ice charts are always a good problem-solving strategy for organizing your information. Okay. So I start with no ions, and as my solid dissolve, I'm going to generate some ions, and I'm going to use X and 2X. They need to match the mole ratio there, so here's my value at equilibrium. And we ignore the solid because it's a solid, so it doesn't get included in the K expression. But you can, if you're thinking about the change in my solid would be negative X, right? So X represents how much solid dissolves. That's one way to think about it in this context. Therefore, we call X the molar solubility. So solubility is what we use to describe how much of something will dissolve. Molar meaning we're doing that in terms of molarity. So if a question asks you to find the molar solubility, they're basically asking you to solve for X in this kind of ice chart scenario. So I've got my ice chart I've already got my K expression written over here, so it's calcium times hydroxide squared. So if I plug these things into my K expression, I end up with calcium times my hydroxide concentration squared. That is 4x cubed. And then my K value I'm getting from the table right here is 4.7 times 10 to the negative 6th. So I'm going to rearrange and solve for x. So x is the cube root of 4.7 times 10 to the negative 6 divided by 4. And I believe that ends up giving you 0.011 molarity. I'm doing that to 2 sig figs because my K value is to 2 sig figs. So that's why I'm rounding it that way. So that's an example of how you would use K to solve for molar solubility. Now let's look at a different type of problem. If we scroll down here, this is an example where you are going to find K given concentrations. So for number 6, actually I realized you're not actually necessarily given the molar solubilities. Oops, this is a typo. I should just say it should just say given ion concentrations. So that is a typo there. Sorry. So let's think about what this equilibrium system is. We've got lead iodide, so it's solid lead iodide. It's going to dissolve and form these ions, lead and 2 iodine right there. I can set up an ice chart for it. We ignore the solid because it gets left out of the K expression. Let's write our K expression over here. So it's going to be lead times iodine squared because coefficients become exponents. And if we take a look at what the problem tells us, it tells us the concentration of iodide in a saturated solution is this right here. So that means my equilibrium value of iodine is 1.25 times 10 to the negative third. So that means, and these both start at 0, that means my change is 1.25 times 10 to the negative third. And if I know one value in the change row, I should be able to figure out all of the other values because I just used my mole ratio. In this case, it's a 1 to 2 mole ratio. So my iodine value is double that of my lead value. So my lead is going to be 1/2 of 1.25 times 10 to the negative third. So this is going to be 1/2 of 1.25 times 10 to the negative third. So I'm going to go and plug that into my K expression. So this is going to be, let's see, my lead is 1/2, so it's 1.25. I'm going to plug this in my calculator, E negative 3. Divided by 2, so this is going to be 6.25 times 10 to the negative 4, and this is 1.25 times 10 to the negative 3, and that's going to be squared. So we plug 1.25 second E, negative 3, 25 second E, whoops, second E, whatever you get here, negative 3, sorry, something on the calculator. You should be getting 9.77 times 10 to the negative 10th, I believe. Excuse my calculator errors if there was one. I'm going to report this to 3 sig figs because it's a multiplication problem and my original values both had 3 significant figures in them. And so that is how you would solve for KSP given concentration values. So you just have to be really careful to read the question carefully and say, like, what is it telling me? Is it telling me X or is it telling me 2X? You know, what is this problem telling me? Okay. Thank you.